All right, standard electrode potentials. Turns out that the measured EMF, the measured cell potential, is can be calculated as the sum of the electrical potentials of the two electrodes. E naught cell, E naught meaning standard conditions, so E naught cell, the entire cell potential is going to equal the potential for the oxidation reaction to occur plus the potential for the reduction reaction to occur. But we have a problem because the oxidation would be, say, with our zinc one, it would be the zinc solid zinc 2 plus reaction is the oxidation. How likely is that? How likely is zinc solid to give up 2 electrons compared to how likely is copper 2 plus to take in 2 electrons? But we can't measure them individually. We can only get an electrical current, we can only get the cell voltage if you have a cathode and an anode hooked together. And so what we decided to do is we said, let's make our own electrode here. Let's make an electrode, and we're going to call its individual potential 0. Let's make an electrode, and let's say this electrode has 0 volts in terms of its reduction potential or oxidation potential. We just made an electrode and called it 0. Can you do that? Can you just make something and say it has 0 potential? Well, yeah, we do it all the time. For example, if I had a situation where I had, say, a ball sitting up here on top of this cliff here, and I said, okay, I want to know the potential energy of this ball. Well, how would you calculate the potential energy? Oh, we remember from physics that potential energy equals mgh, the mass of the ball times the acceleration due to gravity times the height. Well, what are you going to use as the height? Well, the easiest thing is, say, if this is, say, 2 meters above the ground, we'll call this 0 meters because it's the ground. And the difference between 2 meters and 0 meters is, well, yeah, it's 2 meters. But question, why did we set the ground at 0 meters? Because it was convenient. But what if the turns out the cliff went further down here? Can we see that this ball has more potential energy up here if we're looking to see how much potential energy it would be if it went all the way down to here? But the question is, I don't want it to go down to here. I just want to measure this potential energy here. Can you see that it's easier to just call this the 0 point, the 0 potential energy point where the ball ends? If the ball ends here, let's call this a 0 potential energy point because then it makes our calculations easier. We set 0 potential energy. Whenever we're looking at objects falling, we find where they're going to fall to. We set that as 0. All right, so we are fine with setting a 0 potential energy as long as everyone knows, yes, there could be a lower spot, but since we're not going to that lower spot, we're only interested here. So with our standard electrode potentials, we just had to create an electrode and tell everyone we're calling this 0. And you can do that. Bad news, we won't get into it this chapter, but different people like different 0 electrodes. And so when you're actually doing electrochemistry, if you're doing research, you have to tell people what you call the 0 electrode. A lot of people use the SHE electrode that we are going to use here, but SHE electrode has some issues in terms of it's just not a very practical electrode. It's not the easiest one to make. And so there are other electrodes that are easy to make, such as silver chloride electrode that people use instead as the 0 point just because it's easier to make. The good news is you can call it 0 as long as you tell everyone else, okay, this is what I'm calling my 0 point. Just as here, well, since I'm measuring this, I'm going to call this my 0 point. Someone else might want to call this a 0 point, but I'm telling everybody this is what I'm going to call my 0 point. In general, we tell everyone for our cell electromotive force, the SHE electrode is our 0 point. Okay. So let's look at this. That was too long of an introduction. This is our standard hydrogen electrode, SHE, standard hydrogen electrode, where in this beaker we have 1 molar HCl. We then have this glass container here that's open on the bottom and open here where we put in H2 gas, hydrogen gas, at 1 atmosphere pressure. Sticking down through here is a piece of platinum. This is platinum wire with this platinum mesh here. And that's our platinum electrode. The nice thing about platinum, it is inert. We cannot oxidize it. We cannot reduce it at normal potential values. So it can't be oxidized or reduced. The only thing here that can get oxidized and reduced then is the H plus, which is in the +1 oxidation state, or the H2 gas, which is in the 0 oxidation state. So it's really an oxidation reduction reaction between H2 in the 0 state and H plus in the +1 state. That's the redox reaction occurring. All right. And so when we look at that reaction, 2H plus, 1 molar plus 2 electron goes to H2. Since this side, the reactants are gaining electrons, this is reduction. We're going to say E naught reduction, the standard reduction potential is 0 volts. We are calling it 0. Why this is not the easiest one to make is because H2 gas, you have to have a bottle of H2 gas, you have to have a pressure meter to make sure, a regulator to get only 1 atmosphere. H2 gas plus oxygen gas can get explosive, so that's a danger there. You need a lot of precautions here, but it's a very nice electrode and it's a very good 0-point electrode. So that's what we use, standard hydrogen electrode. So what we're going to do, since we've got that as 0, we are going to then hook up the standard hydrogen electrode to measure the potentials of our other electrodes. So, for example, that zinc electrode that we had, let's do that. Let's make our zinc half cell. We'll call it the half cell here, where we had a solid piece of zinc and 1 molar zinc sulfate in water. And let's hook that up through a wire and through a salt bridge to the SHE, where we've got our 1 atmosphere hydrogen gas, 1 molar HCl. And make sure it's 25 degrees, standard conditions. And when we do that, we find the mass of this zinc electrode is decreasing. We see that this mass is going away. So what must be happening if solid zinc is going away? Well, it's becoming zinc 2+. Solid zinc is becoming zinc 2+. Therefore, the mass of that solid zinc is decreasing. So this must be oxidation. Oxidation is happening here in this situation. So note, oxidation did happen with our at zinc when we had copper electrode over here. Oxidation is also just so happens to be happening here with our SHE electrode too. So our cell diagram is zinc solid, phase change, zinc 2 + 1 molar, salt bridge, H plus 1 molar, phase change H2, 1 atmosphere, and another phase change, platinum solid. And when we do that, our voltmeter up here reads 0.76 volts. Okay. Cool. So, what that tells us then, here's what we're getting to. Here are 2 reactions. Our anode, the oxidation, is this reaction, and it has a certain electropotential of oxidation. And here it happens to be 0.76 volts. Our cathode, well, it has a, pardon me, we haven't gone there yet. This has a potential. The cathode, this reaction also has a potential, and if we add the 2 reactions together, we should get the overall cell potential. So the amount that this piece of zinc wants to give up the electrons compared to how much this hydrogen wants to take in the electrons gives us our cell potential when we move these through. Since oxidation is happening at the zinc electrode, that is E naught ox. Since reduction is happening at the SHE, that's E naught reduction. Recall E naught cell equals the oxidation potential plus the reduction potential, but also we measured E naught cell when we hooked this together. The voltmeter up here read 0.76 volts, so we know the whole cell potential. But recall that we set the reduction potential at 0. This is SHE, our standard hydrogen electrode. We set its potential to 0, so 0.76 volts is going to equal E naught 0, the oxidation potential, plus 0 for the reduction potential, which tells us the standard reduction potential for zinc, the standard oxidation potential for zinc. Note, the standard oxidation potential is 0.76 volts. If you flip the reaction, if you make the reaction go the other way, you just change the sign of the voltage. So we found out here that zinc solid going to zinc 2 plus 2 electrons, this oxidation has a voltage of plus 0.76 volts. That's what we got down here. But the question then is, okay, what's the standard reduction potential? What if you had zinc 2 plus and you wanted to add 2 electrons to it? What's this reduction potential? It's just the opposite sign. So the reduction potential for zinc E naught reduction would be negative 0.76 volts. So, recap. When we set this up, put a zinc electrode next to SHE, we found out that oxidation was happening at the zinc electrode. Since the SHE adds nothing, 0, to the potential, we know that the voltage reading that we got by setting this up, that voltage reading, 0.76 volts, equals the oxidation potential of that zinc electrode for this reaction that's happening. If we reverse this reaction to change it to a reduction potential, then we just change the sign from positive 0.76 volts to negative 0.76 volts as the reduction potential for the zinc electrode compared to SHE. All right, now let's do the same thing with copper. What about that copper electrode? Well, we're going to then hook up the standard hydrogen electrode to a copper half reaction, the beaker with a copper solid and the copper 2 plus, put in the wire, put in the salt bridge, and we find the mass of the copper electrode is increasing, which means reduction is happening, which means that's the cathode. Our cell diagram, we always start at the anode. Cell diagram would then be platinum solid, phase change, H2 gas, 1 atmosphere, phase change, H plus at 1 molar concentration, salt bridge, copper 2 plus 1 molar, phase change, copper solid. We know this is the anode. This is the reaction happening at the anode. This is the oxidation, but we know the reduction reaction is 0 volts. So the oxidation reaction is just the negative of that. Well, what's a negative 0? Well, negative 0 is still 0. Yay, that's still going to be 0 volts. But here's our overall reaction. We know the E naught cell is going to be the oxidation potential plus the reduction potential. This cell reaction here, the voltmeter read 0.34 volts. So 0.34 volts equals the 0 oxidation potential plus our copper reduction potential. Therefore, the standard reduction potential of copper is 0.34 volts. Which means when we add these up, we know our zinc oxidation potential was 0.76 volts. Our copper reduction potential is 0.34 volts. Recall, I'll write it again. E naught for the whole cell equals the oxidation potential plus the reduction potential. Therefore, we take the oxidation potential of the zinc plus the reduction potential from the copper, add it up, and we get 1.10 volts for this reaction. Which means if you actually did have a voltmeter, if you actually had a voltmeter, and here's our original galvanic cell with our zinc electrode and our copper electrode, this voltmeter would read 1.10 volts. Because, assuming our 1 molar concentrations, because that is our cell when we look at the oxidation potential plus reduction potential. And that's what it would read. All right. Cool. So then someone decided, that's nice, but what can we do with this information? Someone said, you know what I like to do with a bunch of information I get? I like to make tables. And so in our next video, we'll look at tables of standard reduction potential.